Good afternoon, everybody. Sorry for that delayed start to the presentation. For me, it's a pleasure to present to a medical community. I'm from mechanical engineering, as was said earlier, and it's not often that we do have this interaction. But as Richard said, we have been working on quite a number of projects, and it shows that in many areas, as hopefully I'll show in the brief presentation I have, that really to be able to succeed, we need to be able to work together depending on the perspective that we are coming from. Next slide, please. So we will focus on the area of oxygen availability, and this is something which right now COVID, of course, has made it crucial, but we were looking at this primarily from the context of non-communicable diseases, the need for oxygen therapy for the various other non-communicable diseases, but of course it is a cross-cutting issue as well. And one of the things that attracted us to this is the fact that it affects children quite a bit, and it's a major risk factor for death amongst children as well. Many ways a hospital can get oxygen, either the large oxygen plants that are built at the hospital itself, through oxygen cylinders, or through smaller oxygen concentrators. Just for the audience, the larger plants that you find being built at hospitals are just simply large oxygen concentrators, and then use that to fill the oxygen cylinders on site. Next slide, please. In a low resource setting, is that although hospitals say they have oxygen, the supplies are often limited due to lack of resources, sometimes just to fill the oxygen cylinders. In Kenya, as you saw a few months ago, just lack of the cylinders themselves. And even those who have oxygen concentrators, a lot of them tend to be broken. Next slide, please. So what we're trying to achieve through this interaction is how can we get oxygen, make it more available to our community, especially in rural areas, but with equipment that is high quality and user-friendly, that is also targeted to the environment within which they operate. These tend to be hot, dusty, humid. And again, most of the equipment you can buy were not designed or built for these environments, and they end up breaking down relatively quickly. Another key thing that you find in the literature is that most of these equipment will break down, all the equipment does, but then they're not easy to repair, simply because there may not be adequate staff qualified to repair them. And the issue is this: different manufacturers make the equipment in slightly different ways. And you can find even a single hospital has equipment for multiple manufacturers. So it's unlikely that even that staff member on board would be able to repair all the various different types that are there. And even when they can, spare parts tend to be very difficult to come by. Especially when we're talking about the oxygen concentrators, a lot of them in our hospitals were donated. So they come from many different countries. During that process of donation, the issue of maintenance and spare parts was rarely in the conversation. But what we're saying is, because these equipment run pretty much 24/7, there need to be a pipeline to make them easy to repair when they do break down. And a key factor of that is the availability of the spare parts. Oxygen should be affordable to patients. And that's one of the basic premises that we are coming from. Because where you find it's expensive, you either have the patients discharging early because they can't afford it, or a lot of times not even getting the treatment they need because they simply can't pay for it as well. Next slide, please. So before we embarked on our project, we wanted to find out that what is the current status of oxygen availability in Kenya. So in November last year, 2020, we carried out a survey within 11 counties, and we surveyed over 210 hospitals across the 11 counties. And we just asked them those basic questions that you see on the screen. Question number one, do you have oxygen for the patients? If the answer is no, the survey ended, right? If you do, then the next question was in how do you have it in all the forms? Is it cylinders, piped oxygen, concentrators? And then depending on the options you pick, we asked what are the main challenges you're facing with the cylinders? What are the main challenges you're facing with the concentrators? And the last question, we just wanted to have an idea of, for those who charge for oxygen, how much are you charging? So again, here we're looking at the patient price, not the cost of the hospital. What is the price that the patient actually sees? Next slide, please. Oh, next one. There we go. Oops, sorry, just go back one, please. Ah, it's blank. Okay, next, let's go to the next one. Seems to have skipped a slide. So when we looked at the different sources of oxygen that you find within, we found that it's a mixture. The lighter green is what is the private hospitals, the bluish is the public, and by far those who actually have oxygen, the highest percentage is piped oxygen for those who actually have it, more in the private hospitals, about 50%. And remember, here's a case where I can have multiple of them, not just one. So the top ones are those who have concentrators only, cylinders only, piped oxygen only, and the lower ones are the different combinations. Next slide, please. We also asked them, what are some of the challenges that they are facing? And those who have oxygen cylinders, and these were 72 who expressed challenges, the number one was simply the availability and access of oxygen for the cylinders. Some of the answers that were given, there were long periods between refills. So I have cylinders, but they're empty. Others were inefficiency in getting a new supply of oxygen. So that was the number one challenge. The second challenge was that they ran out relatively quickly. And of course, this is a frustration if you're constantly changing oxygen cylinders as well. The third one, as one can expect and has seen them, is that they are heavy, difficult to move from one place or another, or carry, or portability. And the last major, there were others, just the four top ones, was simply the cost. Sometimes the cylinders or the oxygen runs out, and the hospital doesn't have funds at that point in time to order the refill. Next slide, please. Those with concentrators, the issues were a little bit different. The first one were maintenance issues, and this is also supported in what you find in the literature. And this is simply the fact that they fail to produce the level of oxygen that you require, or they simply malfunction, and they have to wait until they are repaired. The second one, as one would expect, is the loss of electricity. These are plugged in. When power goes, they stopped working. Most hospitals, the backup generators, when they have them, is only a certain part of the hospital. It's not every socket. And sometimes then, even if you have a backup generator, you have to move the patient and move the concentrator to a part of the hospital that is backed up as well. The other major challenge they felt with them is most of them are designed for one person, maybe two, and therefore you need quite a large number of them to be able to serve a large number of patients. And of course, that similar challenge applies with oxygen cylinders. And the last one was just simply the cost, that they're expensive. But as I mentioned, the majority of them are actually donated as well. But for those who bought them, the cost was expressed as a major challenge. Next slide, please. So the issue of how much does oxygen cost? Over half the hospitals don't charge, 53%, so they don't charge for oxygen. And about 50% or so, 49% do charge for oxygen. What is interesting was the range of what is charged to the patient. It went all the way from 9 of them charging anywhere between 500 to 1,000 shillings, all the way to 6 of them charging over 30,000 shillings. This is for 24 hours of oxygen, yeah, independent of the source of the oxygen. Yeah, so you see this huge gap between the lower end and the upper end. Initially, we thought that this was public and private, but you find that some private on the lower end and some private, actually most private are the ones also on the higher end. Next slide, please. There's one slide, I think the blank one, maybe I'll just verbalize it. I'm not sure why that slide was missing. But the blank slide was starting off the point of who has oxygen. And we found that about 49% of the 200 plus hospitals, and here we're surveying level 2 and 3 hospitals only. Our assumption was that a level 4, 5 will have oxygen. This is just 2 and 3. About 49% did not have any oxygen at all. So those percentages you were seeing on pricing and so on are for the other 51% who actually have oxygen. And of those 49% who didn't have oxygen, the majority were government hospitals. And again, one can speculate on the reasons for that. Informally, again, many of the respondents were unwilling to give us official reasons for obvious reasons of victimization, etc. But what was coming out was that being free makes it not be there. The fact that many are required not to charge for oxygen as a public hospital means the resources available to the hospital are lower. When it runs out, and they just don't have it, simply because of lack funds to do that. But again, that is anecdotal. We didn't get hard data on that. So part of our task, therefore, was, can we come up with a locally constructed oxygen concentrator? So it's design, build, prototype, medical grade oxygen. It needs to be robust, easy to transport, store, and use, easy to maintain, meets all the World Health Organization standards, and it's green design, which in our context is the minimal use of plastic. Most oxygen concentrators now you get, the casing and most of the structural components inside are plastic, which means at end of life, you now run into a disposal issue. Next slide, please. So here is, and we're using students as well with our team. So here is what the concentrator looks like, both on the outside and the inside. The components were sourced from various vendors as well. The casing, the structures, and putting it all together was all done at the University of Nairobi. We chose to have a metal casing. The idea being simple, that you can take parts in and out as they break. And when you reach end of life, you can either recycle the entire casing as metal, or you can put in new components and continue use in the same original steel casing. It was designed as a trunk, which closes on the top. So it's easy storage, easy transport, dust-proof, etc. So all access is from the top. Next slide, please. We're able to run it. Here's just a chart of one of the initial flow rates of oxygen concentration versus flow rate. We're able to get those much higher. These are some of the initial ones that we're just testing out that everything works. Next slide, please. Then we had a stakeholder engagement on this with members from the medical community in December. They made several suggestions on the design. The key one was on the orientation, that the original just occupied too much space. The original also required you to carry it. It didn't have wheels. The current design, we literally just flipped it on its side to a large degree, reoriented parts on the inside. It now has wheels on the bottom as well. So this is the current design that we are finalizing based on the design changes that were suggested from a stakeholder engagement in December. Next slide, please. I think it's the last one. And so where are we? We are also creating a version in that design that has a lithium-ion battery pack backup in it. So it should be able to run for up to 8 hours if the power fails. The backup version, because of the type of battery being used, lithium-ion allows you to have high energy density. In simple words, it means that it's a small package, but can store a lot of energy in it, as opposed to conventional other batteries. But it also costs a lot more. But our view was that the size is important. You don't want something very big. At the same time, being able to run for 8 hours should be hopefully be sufficient for power to be able to come back as well. But it does increase the price, the cost, by about 50% for that particular version. We are finalizing the design as we speak. It should be done by end of next month. It's in the what do you call it? The fabrication stage. We have contracted out to commercial fabricators in the industrial area. to do this for us. And then we put it all together. We plan to have another stakeholder engagement in June with the revised design, again, to get more input. If all is well, we'll take it to KEBS for another certification that as are required. We began that process already. Once that is done, which we hope by July, August, that will be complete. And then working again with the medical team, we'll then have 6 devices that we will give out and have them run for several months and see how they pan out before we see then how we can upscale this and be able to produce them in mass. And I think that is the last slide. Next slide. Yeah, thank you.